Hi, my name's Brad. I'm an applications engineer with Keithley Instruments and Tektronix. In this short video, I'll be showing you how you can analyze the noise and power linearity of a DC-DC boost converter using a Keithley 2461 SMU and a Tektronix 5 Series Mixed Signal Oscilloscope. Let's get started.
Here's the setup that we'll be using today. We're using a micro USB boost converter powered by the USB port on the 5 Series MSO. Since a lot of boost converter behavior only shows up under load, we're going to be using a 2400 series graphical source measure unit to sync current from the converter output, specifically a 2461 SMU. By using the SMU to measure voltage and sync current at the same time, we'll be able to view the converter's power linearity. For looking at noise, we're going to be monitoring the input stage of the converter with a 5 Series MSO. Of course, you could also view noise on the output with a separate channel, but I'll leave that to you. Let's start by configuring the SMU. Starting from the default settings, we'll first have to change the function from sourcing voltage and measuring current to sourcing current and measuring power. The SMU will actually measure voltage but do the power calculation for us. Notice that we're measuring overflow watts. We'll need to adjust the voltage limit to something higher than what the converter is outputting. 20 volts will do. By turning the output of the SMU on, we can actively force 0 amps and make the SMU a very high impedance instrument. By setting a different current level, we can see the power measurement increase as the SMU is now syncing 120 milliwatts. Both the power and current are negative here since we've connected the converter's high terminal to the SMU's high terminal. Positive values would indicate we're forcing power through the converter in the wrong direction. Let's now configure a current sweep to see how the converter responds to different current drains. We'll be configuring a dual linear sweep to sweep from 0 amps to negative 600 milliamps and back again. Remember to make sure the current is negative, otherwise you'll blow up the converter. We'll be defining the sweep based on the number of points in it. 50 of them should be fine for us. We'll have the sweep run twice just to be sure of our results. We could have it run forever. Finally, we'll tap Generate to create and load the sweep into memory, then press Trigger to execute it. Let's go over to the graph screen and see how the power output from the converter is responding. The graph has automatically placed current on the horizontal axis since that's what we're sweeping. The power looks very linear up until about 6 watts where there's a drastic discontinuity. We'd better not use this supply for a device that needs more than that. Now that we know about the power this DC-DC converter can deliver, let's take a look at the noise on it. Again, starting from the default settings, I'll press the Auto Set button and let the 5 Series MSO find the signal for me. Even with the SMU not drawing any power, it still looks like a pretty nasty signal. I'll clean it up a little bit and scale out. Let's trigger the SMU's sweep again and see what happens. Yep, we get a lot of ripple, and remember that this is just on the input stage. As the second SMU sweep happens, these signals look pretty long. I could spend more time using the 5 Series' advanced triggering features, but I think I'll scale out again first to 100 microseconds per division, and then I'll start the SMU sweep again. Well, we can see a bit more noise, and whoa, what was that? I'll move the trigger level and set the 5 Series to capture a single event. I suspect this is the power discontinuity we saw earlier, but even before that we're still seeing 2 volts of ripple. After seeing the power linearity and the noise of this device, maybe it's time for a new converter, or maybe not. Maybe we need to do some more testing.
For more information, please visit tech.com. Thanks for watching.